In this lecture, we are going to study the folded cascode op-amp a little bit further, because there are a few more things to understand about the folded cascode op-amp. The three major quantities that we still have to look at are the slew rate of the op-amp, the noise, input referred noise, and the input referred offset. And finally, we need to build the data sheet of the op-amp in an organized manner as a table. So let us first start off with each one of these one by one. So the folded cascode op-amp that we'll draw is an NMOS input pair folded cascode op-amp. We will assume this has the high swing cascode on the NMOS side. So let us number the transistors. M1 and M2 are the input pair. M0 is the current source. M3 and M4 are the common gate transistors. So they have a gate bias voltage of VB3. M5 to 8 form the NMOS current mirror at the bottom. And there is a bias voltage VB5 at that gate, and finally M9 and M10 are the current sources, and they have a bias voltage VB9. Let us assume that the output has some load capacitance CL, and the output is taken at the common drain node between M4 and M6. We have seen the structure before, so let us now look at the slew rate of this op-amp. To look at the slew rate, let us quickly review what slew rate is. So when you are looking at the slew rate of the op-amp, for example, you might be in unity gain feedback and you are driving a capacitive load, let us say, and you apply smaller and smaller, larger and larger input steps, and it turns out at some point of time the output will not be able to follow, and eventually the output will not be able to follow in a small signal fashion, and because there is a certain limitation on the rate at which the capacitance CL can be charged. That is given by the maximum. So when the input step gets really large, the output current of the op-amp cannot support such a large rise time, and there is some maximum output current that the op-amp can deliver, and at this stage the output rises linearly. So the output rises linearly, and more importantly, any larger input step will not allow the output to rise faster than this ramp. Now this is this is called the slew rate of the op-amp. Now we have seen the slew rate of the regular 5 transistor one stage op amp as well as the telescopic op amp. So let us quickly look at the case for the folded cascode, because there is one small difference between the folded cascode and the other op amps. So let us assume that the total current through M0 is some 2I0. So therefore, in regular bias conditions, the two currents are I0 each. Let us assume that the current through I9 and I10 are I9. So I have a current I9 through I9 and I10. So based on the value of VB9 that I choose. And of course, the bias current through M3, M5, M7 and M4, M6, M8 are each going to be, so let me call that I3. So I3 is simply going to be I9 minus I0. So this is going to be the design condition, the bias point for each of these transistors. So I3 flows through M3 to M8, these 6 transistors. So clearly I9 has to be larger than I0, as we have seen. So now let us assume that for this particular op amp, we apply a very large input step. So in other words, the input differential voltage has a very large step. So delta VD at the input. When this happens, let us assume this is a positive step, so that the gate of M1 goes very high, gate of M2 is pulled very low. When this happens, so let me show that in blue color. So delta VD by 2 and minus delta VD by 2, so that there is a large delta VD at the input. When this happens, the current through M1 will become 2I0, the current through M2 will become 0. So if delta VD was large enough, all of the current would flow through M1 and there will be no current through M2. So now what happens let me call these two nodes, node X and node Y. If you look at node X, there is a current entering which is I9, and there is a current which is leaving which is equal to I3 plus I1. So KCL at X tells you that I9 is equal to I1 plus I3, where the subscripts denote the drain current of transistors corresponding to those numbers. So in other words, ID9 is equal to ID1 plus ID3. Now I9 of course is fixed, and now the current entering M3, so ID3 now is equal to I9 minus 2I0, because I0 happens to be the original bias current through M1 and M2. Now all of this total bias current 2I0 flows through M1. So the important condition to note is that if I9 was less than 2I0, M3 for example would get cut off because it cannot support reverse currents, and naturally what this means is that Vx and Vy would fall to push M1 into triode region. So that would be the progression. This is not something which is desirable. So you need to ensure that I9 minus 2I0 is greater than 0. So but of course we do not want to burn too much current, so therefore typically I9 would be off this maybe approximately 2I0 and slightly greater. So you have to ensure I9 greater than 2 I0, but you can just make it slightly higher than 2 I0, so that no transistor leaves the triode, leaves the saturation region. So this is something to be ensured. If this happens, then you will have to find out what the total current through the output node is. So let us assume that I9 is greater than 2 I0, in which case the current through M3, M5, M7 is equal to I9 minus 2 I0. And what happens to this current? This current, of course, gets mirrored through M8 and M6. So this current is clearly I9 minus 2 I0 flowing downwards. Now what happens to the other path? M2 is clearly cut off. Therefore, the current I9 now completely flows through M4 and M10. There is no current I0 that is being pulled out of Y into the input stage. So this current is 0. Now this means that a current 2 I0 flows through the load capacitance, and therefore the slew rate is equal to 2 I0 over CL. So this looks similar to that of the 5 transistor 1 stage op amp as well as the telescopic, but please note, because there are extra bias currents in the circuit, you have to be a little bit careful when designing this particular op amp for slew rate. Finally, we need to look at the noise and the mismatch. So let us quickly look at noise. As you might imagine, we are just going to write down the expression for noise because we have studied what happens in a single-ended folded cascode. So we know what happens when you convert it into a differential structure. So we should now be able to write down the expression. So you now have 11 sources of noise because you have 11 transistors. So let us quickly write down each one. So let us look at them in turn. M0, noise of M0 splits between the two parts equally and therefore appears as a common mode noise at the output and gets cancelled. So there will be no noise current flowing through the output. As always, you can either look at the short circuit the output and look at the output noise short circuit current and divide by the transconductance of the op amp, or you could look at it at no load condition and look at the divided by the voltage gain to get the input referred noise voltage. Either one of these will give you the same answer. So noise of M0 goes through identical paths, especially at low frequencies, and therefore gets cancelled. You assume that the two paths are identical. What about M1 and M2? Of course, the noise of M1 and M2 follow the exact same path as the signal and do appear at the output. And similarly, noise of M9 and M10 do appear at the output. What about noise of M3 and M4? At low frequencies, they do not produce noise. I again point out that this is true at low frequencies, at high frequencies, because you have parasitic capacitances at the different nodes, the noise from the cascode transistors can appear at the output. So I will leave that as an exercise, as a homework exercise for you to look at for a simple single-ended cascode. You can also look at folded cascode or a regular cascode. For both of these transistors, you will see the same effect at high frequencies. Similarly, transistors M5 and M6 will not have any noise at low frequencies because these are cascode devices. And M7 and M8 will produce noise. Therefore, you will find that the output short circuit current will consist of 3 portions. So you will see IN1 and 2 plus IN9 and 10 plus IN7 and 8. And clearly, these noise sources will not be correlated. Each one of them produces independent noise, and therefore the output referred noise, thermal noise density, will be 8 kT by 3 GM1 plus 8 kT by 3 GM9 plus GM7 times 2, because you have M1 and M2, M9 and M10, and M7 and M8. So this noise is 16 kT by 3 into GM1 plus GM9 plus GM7. Again, a reminder that as far as noise is concerned, the drain noise is not injected symmetrically into the input, into any of these nodes. You cannot use differential mode analysis to solve for noise. I'm just pointing that out there. So the input referred noise density would be En squared over delta F would be divided by the square of the transconductance. So this is clearly 16 kT by 3 GM1 squared into GM1 plus GM7 plus GM9. So this is the input referred noise of the folded cascode op-amp. Now I want you to compare this to the telescopic op-amp, and you will find that there is an additional source of noise from the PMOS transistors M9 and M10. Therefore, you expect the input referred noise, the noise performance of the folded cascode op-amp to be slightly worse compared to the telescopic op-amp. This is because of the additional current sources M9 and M10. Similarly, if you were to look at mismatch, we are going to assume only VT mismatch exists. And you are trying to find out the input referred VT mismatch. So as you might expect, the mismatch of transistors M1 and M2 would appear directly at the input of the folded cascode op-amp. So the expression for the input referred offset sigma squared OS in is going to consist of several different expressions. It would consist of the input referred offset of M1 and M2 appearing directly, and you will have two more expressions. As you might imagine, the mismatch between cascode transistors M3, M4 and M5, M6 do not appear as an input referred offset at the input. We have seen this effect before, and even for the telescopic op-amp, and therefore the other expressions you will get will now depend on VT 7 and 8 and 9 and 10. As you remember, as you might imagine, the VT mismatch between M7 and M8 looks very similar to that of a telescopic op-amp case, and will be scaled by the ratio of the GMs of M7 and M1. So that is the case for this transistor and these two transistors. And finally for M9 and M10, again their offset voltages are expected to be scaled by the relative ratios of GM9 and GM1 the whole square. Now we have simply written this down. I want you folks to go ahead and figure out, check if this is, check this expression. I have just written it down based on intuition. You need to figure out whether this intuition is correct or wrong. In other words, whether VT7 and VT8 will appear as scaled by GM7 over GM1 the whole squared, and whether VT9 and VT10 will also be scaled by GM9 over GM1 the whole squared. So this is going to be a general homework exercise for all of you. Now we are in a position to write down the data sheet of the op-amp. So we are able to compile the different expressions. We will follow the same set of expressions as we have derived so far. So the first thing you want to know about the op-amp is the DC gain or the low frequency gain. That is clearly going to be GM1 times RO, and RO is clearly you have two portions. So the first portion is R up, which is GM4 RDS4 times RDS9 parallel RDS2 in parallel with, so that is the path looking upwards. So you have GM4 RDS4 times the impedance looking upwards, which is RDS10 in parallel with RDS2. And RDS9 is the same as RDS10. And looking down, you have a GM6 RDS6 times RDS8. And as we have seen, this is slightly lower than that of the telescopic op-amp by an order of 2 or 3 times. The next parameter is the unity gain frequency, omega u. This is simply going to be GM1 over CL, where CL is the load capacitance at the output node. It is the sum of the load capacitance and the parasitic capacitances. And the third expression is the expression for the non-dominant poles and zeros. As we have seen, this op-amp is going to have several non-dominant poles and zeros. For example, if I look at the path the signal takes from M1, so that signal goes through node X, this node, this node, this node, and this node. So clearly, you are going to see at least 5 poles for this particular circuit. So you are going to have several poles and zeros. And as I mentioned, this is a homework problem for you to analyze as to see how many poles and how many zeros you have from this particular op-amp. The fourth expression is going to be the input referred noise, which we have just calculated. The input referred noise of the op-amp is going to be 16 kT by 3 GM1 squared into GM1 plus GM7 plus GM9. As I pointed out before, this is going to be slightly worse than the that for the telescopic op-amp. And the input referred offset is going to consist of the offset of VT1 and 2 directly appearing at the output, and you have scaled versions of VT7 and 8 and VT9 and 10. The next parameter that we need to look at is the slew rate. As we have seen, for this particular op-amp, the slew rate is going to be 2I0 over CL. The input common mode range, we have seen this. The input common mode range is decided by when M0 goes into triode and when M1 goes into triode. So as the voltage keeps decreasing, M0 will eventually hit the triode region when the input common mode range is VDSat0 plus VGS1. And as the input common mode increases, so what will happen is that Vx is constant at VB3 plus VSG3, and the input can go one threshold voltage above that particular voltage. So that is nothing but VB3 plus VSG3 plus VT1. So the maximum voltage at the input can be VB3 plus VSG3 plus VT1. The output common mode range is, of course, depends on the output common mode range, of course, depends on the values of VB5 and VB3. The minimum value occurs when M6 hits the edge of the triode region, and that can happen when the input voltage goes 1 VT6 below VB5. And if the output common mode increases, that will cause M4 to go closer to the triode region, and that can happen at a voltage VB3 plus VT4.